All right. Thank you so much for having me here. It's great to be here. I'm very excited to tell you about this recent work with Krishna Rajagopal and Urs Wiedemann on dynamics of heavy quarks in hot Yang-Mills plasmas. And as you can see from the subtitle, and as Lance pointed out in the previous talk, the reason why I'm going to be able to make concrete progress and show you a calculation is because I'm going to use n equals 4 super Yang-Mills. However, I could have chosen another title for this talk, more in line with the program in which this conference is embedded, which is what is Brownian motion in the particle theory version. And why am I suddenly changing topics right away to a very old problem in physics? Well, let me make this digression. So Brownian motion, the way I think about it, or for purposes of this talk, you can think of it as the dynamics of a heavy particle moving through a fluid. So you have some particle that you're following, and due to the vibrations of the fluid, it receives random kicks that move it around and essentially make it diffuse. If you want to make this mathematical, what you'd write down is a Langevin equation. You'd say, I have a random force that's driving the motion of this heavy particle, and essentially how the particle interacts with the fluid tells you something about how the fluid transfers momentum to this heavy particle. So you can think of using this heavy particle as a way of learning about dynamics of the fluid surrounding it. Now, back to particle physics. You can actually set up a very similar problem using standard model degrees of freedom. You can think of putting a heavy quark in the middle of quark-gluon plasma and asking how it moves around. And in principle, there's no reason not to expect something like this. Of course, I have to go through a whole lot of details to actually be able to arrive at a stochastic description such as this. But the idea is that this is a problem that you can set up in the standard model. And this is not only a purely academic question, this is actually something that's relevant in heavy ion collisions. So if we put that heavy quark surrounded by a plasma in a setup that's generated in a heavy ion collision, which if you've never heard of this, DLHC does these all the time. BNL has done them as well. And what you do, or what experimentalists do, is that they take two heavy ions and collide them head-on. Since they're very Lorentz contracted, they're very relativistic, you saw two flat sheets colliding on top of each other. And after they collide, essentially, well, they interact, they form this hot blob of matter that then, because it's surrounded by vacuum, expands, cools down, eventually hadronizes, and we see particles at the end of the day in the detector. Or rather, at the end of some infinitesimal fractions of a second. The infinitesimal fraction of a second that this process takes place in is around 10 Fermi over C, so 10 to the minus 23, 24 seconds. And with this collision, you not only produce this hot blob of QCD matter, you also produce heavy quarks. So we get, by studying essentially the heavy hadrons that we reconstruct in the detectors, you can learn about how heavy quarks propagated through this dense, or to this hot blob of QCD matter. More conceptually, a heavy ion collision starts, well, again, repeating what the video showed, but in a static way so that you can see everything at once. Starts with two Lorentz contracted nuclei colliding on top of each other, head-on. There's some overlap region that then quickly, due to interactions, reaches local thermal equilibrium. This is a whole research subfield in heavy ion physics. And then after that time, once you've reached local thermal equilibrium, you form quark-gluon plasma. And this quark-gluon plasma evolves as a fluid, expands because it's surrounded by vacuum and cools down as a consequence. Then it hadronizes, and then these hadrons eventually stop interacting altogether and free stream towards the detector, decaying along the way if they are unstable. So all of that is to say that I'm going to be looking at this region here. I'm going to be thinking about quark-gluon plasma. And I'm going to be looking at what happens if you put a heavy quark here and ask questions about it. Now, more concretely, I'm going to start with a heavy quark with some momentum p. I'm going to let it propagate for some time. And then I'm going to measure the momentum, let's say. And the momentum of the heavy quark will have changed, could have changed due to interactions with the medium. So I'm saying it's changed by an amount k. And I want to ask, what's the probability distribution for this momentum shift? Simple question. It depends on many things. It depends on the initial momentum of the heavy quark. It depends on the temperature of the fluid. And depends on how much time it's propagated through the fluid. But nonetheless, well-defined question. So what do we calculate? And fortunately, there's a reasonably straightforward answer to that. You can use the heavy quark effective theory Lagrangian to set this up. At 0th order in a large mass expansion for the heavy quark, the propagator for a heavy quark is just a Wilson line. Therefore, the amplitude transition from an in state to an out state is just the Fourier transform of that Wilson line. And of course, you could get higher power corrections in 1 over m, but we're going to be looking at the lowest order result here. So just this is all that you get. And then if you want a probability, you do the same you do in everyday quantum mechanics. You take the amplitude, you square it, and you get a probability density, which amounts in this context to essentially taking this Wilson line, multiplying it by its complex conjugate, tracing, and you get a Wilson loop out of this. This Wilson loop is characterized by a velocity and a transfer separation that's conjugate to the momentum transfer that the heavy quark receives. Okay, so this you would do for a heavy quark in any thermal Yang-Mills bath. You can think of QCD, but you can also think about what happens if I change the Hamiltonian of my thermal environment to something else. So the exercise I'll do today is to think about strongly coupled n equals 4 super Yang-Mills as a thermal bath. And so this is the outline of my talk. I'll spend the first half of the talk telling you what had been done in almost 20 years ago now, studying heavy quarks in this strongly coupled n equals 4 plasma. These calculations, because it's strongly coupled n equals 4, most go through holography. So I'm going to show you the holographic setup that people use to do these calculations. And I'm going to tell you what the conclusion was back in 2006. And not everything added up back in the day, in the sense that heavy quarks didn't seem to be able to reach kinetic equilibrium by just being kicked around randomly through the plasma. And I'm going to tell you how and why that happens. And once I've gone through that, I'm going to essentially complete the calculation. I'm going to, instead of just doing the drag and diffusion calculation, I'm going to do the whole probability distribution that I just introduced. And I'm going to show you that everything is fine. Heavy quarks do thermalize in the way that you would expect. And with that, as a consequence of having an explicit calculation with which to compare, we're going to be able to set up a framework that we'll be able to use in other gauge theories as well. Okay, so heavy quarks in strongly coupled n equals 4. What do we know? Or rather, what did I know when I entered this project? So in holography, well, since I told you that essentially heavy quarks in this limit, you can think about their properties via Wilson lines or expectation values of Wilson loops. Essentially, you need a tool to calculate expectation values of Wilson loop, and luckily the holographic duality provides that. So you can calculate the expectation value for Wilson loop by essentially finding the extremal surface with an Ambugoto action that hangs into the bulk from the contour that defines the Wilson loop. And in this process, you introduce the temperature that characterizes the state of your theory through the metric of the background spacetime in which this string propagates. So the results back in the day looked very intuitive. So you can start by thinking of just having a straight Wilson line and asking what's the extremal surface that hangs from there into the bulk of the holographic description. And you can then ask, okay, how do I identify, say, the mean energy loss of this heavy quark? And you'd say, well, I need to be transferring some energy or some momentum from the boundary into the bulk. And you therefore look at the stress energy tensor flow down the string. That's something that people did and found that the rate of energy loss or longitudinal momentum loss was essentially proportional to the momentum. So you just have a linear drag coefficient that you can calculate, and it's given by this number here. You can do then the same thing for fluctuations around this mean. You can then think about a force-force correlator along the line. So essentially how correlated is one random kick at some time with a kick that the heavy quark receives at a later time. And essentially this correlation will tell you the average, well, the effective diffusion coefficient that this heavy quark experiences. And this is, by the way, it's very much the same that people do to calculate the heavy quark diffusion coefficient from lattice QCD. So what you do there is you set up a Polyakov loop wrapping around the Euclidean time direction. You would insert two plaquettes along the loop, so you take the difference between two ways of taking the winding around the Euclidean time direction. You calculate this in Euclidean time, then you have to work through the spectral reconstruction or the analytic continuation back to real time to actually extract the diffusion coefficient. That's something people still think about, as we heard from Will J earlier in this conference. And you get a result with error bars that are dominated by the fact that you have to do an analytic continuation, which, look, are down here. And you can compare that with the n equals 4, quote-unquote, prediction, which is down here as well. So this is for the case where the heavy quark is not moving relative to the medium, just sitting there and receiving momentum fluctuations. So it's not bad. So this encourages us even more to look at n equals 4 and see what happens here. So same picture here. You essentially insert some field strengths along the line and calculate the correlation function. Out of that, you get that the typical fluctuations in momentum, essentially the diffusion coefficients go like this. They have a very specific dependence on the Lorentz boost factor that will come back to us in a few slides. But the results are there. These were calculated in these papers back in the day. So once you have them, okay, then you can say, let's go back to the first slide, or to the second slide. Let's set up a stochastic description with a drag and a diffusion. So I've separated here the mean, and I've added essentially Gaussian fluctuations characterized by these diffusion coefficients. You can rewrite that as a Fokker-Planck equation for the phase space distributions, so you can convert the stochastic description to the dynamics of the probability distribution, if you want, of the heavy quark momentum. And you get this equation, and then you can ask, okay, what does this equation do? From statistical physics, you would expect that this distribution will at late times reach thermal equilibrium. You'd want a Boltzmann distribution as the late time solution to this. So you'd want that this P goes to exponential of minus the energy, the dispersion relation, divided by the temperature. However, if you look at Gubser's paper from 2006, you'll see that if you try to work this out, this just doesn't work. And it doesn't work because the longitudinal diffusion coefficient grows as gamma to the 5/2, and the drag coefficient is just a constant number. And for this late time solution to be achieved in this equation down here, you actually need what's called the Einstein relation to hold, which is that the longitudinal, which is that the diffusion and drag are related in a given way. And this is obviously problematic if you want to now go to heavy ion people and tell them to use this, because they'll ask, the first question they'll ask, if you're talking to a theorist, is, does this thermalize? And you don't here. So we're going to revisit this. Okay, so I said I'm going to do instead the full calculation of the momentum change distribution, and this is, I mean, interrupt me with questions at any time if you have one. Okay, so this is a more complicated problem, obviously, because now I'm not calculating a couple of numbers. I'm going to be calculating a whole function of k. But the starting point is still the same. I want to calculate the expectation value of a Wilson loop, and I'm going to do this by looking at the dynamics of a string in a higher dimensional spacetime given by AdS5 cross S5. Okay, I have a metric, I have an action, I have boundary conditions. What goes wrong, or rather, what's the complication? Okay, so first I need to be more precise about what I'm calculating. So we're going to be looking at these configurations with velocities that go all the way from purely from a static heavy quark, let's say here, all the way to a light-like heavy quark. And we have this extra parameter in addition to, which is essentially encodes the initial heavy quark momentum, that we also have to deal with. The technical complication that is that I think is something that we just overcame recently is that if you go back to the expectation value I gave you, the Wilson loop I wrote down in the first couple of slides, you actually, if you stare at it, you'll realize it's not the typical time-ordered expectation value that we're used to calculating in quantum field theory. It's rather the product of a time-ordered amplitude with an anti-time-ordered complex conjugate amplitude, and then taking an expectation value over a thermal ensemble of that. That forces you to set up this whole problem on the Schwinger-Keldysh contour. So you have to, so instead of just having one time that goes from -infinity to infinity, you have to start at some initial time, set up a path interval that evolves your system forward in time, but then you have to essentially take a trace to close the time contour. So you have to evolve back. In this evolution, you'll insert anti-time order quantities, and then you have to go down in imaginary time to construct your thermal density matrix. Okay, and luckily for us, we didn't have to think about how to do this in holography. People had thought about this earlier, but later than the calculations that I showed you earlier. And in the holographic side, essentially, the ADS-CFT correspondence is just two ways of rewriting a path integral. So I have one path integral on the field theory side that gives me a Wilson loop. I have another path integral on the ADS side that I'm going to evaluate in the saddle point approximation because I have a strong coupling. And and the action I'm going to extremize is that of the string and because now I have 3 time segments in my Schwinger-Keldysh contour, I'll have one action for one piece of the action here for each one of those segments. Each one of those segments will have a holographic bulk that satisfies appropriate matching conditions that I can talk about more if you ask me about them. And furthermore, since we're going to be looking at the late time regime, and by late times I mean that the length of the Wilson loop is much larger than the inverse temperature, we're actually going to get by dropping the explicit calculation of the Euclidean part of the contour. We're just going to be looking at the real-time segments. And I need to specify a matching condition. How do these two sides talk to each other? And the answer for that is that you essentially the strings have to join at at the horizon of this black brane metric that I described earlier. In pictures, looks like this. You have one side of the Schwinger-Keldysh contour here on the right, a string hanging down from it, and the other side with a string hanging down from it. And on each side, I'm going to have to sum over surfaces such as these that are matched down here at the position of the horizon where the black brane is. Okay, and this is obviously, well, I guess not necessarily obviously, but to do this, you would have to essentially extremize these actions, solve equations of motion, impose boundary conditions, and evaluate back in the action to get the value that you get at the saddle point, which actually can be circumvented just a bit. So just to tell you explicitly what I'm doing, I'm going to parameterize the string in this way. So I'm going to use time and the radial ADS coordinate to parameterize the string, and I'm going to be looking at the profile along the Minkowski spatial coordinates as the things I'm going to extremize. And then I'm going to do one more step, and I'm going to impose the matching condition, not explicitly, but rather I'm going to introduce a Lagrange multiplier. I'm going to modify the action and essentially insert a direct delta by hand by integrating over these numbers Ci that I've just put in by hand. What does that get me? That gets me that this picture that I just showed you becomes now a sum over disjoint configurations. The Lagrange multiplier will enforce that essentially the length of each of these, of the transverse length that these strings go over ends up matching out. So that's enforced up here. But then in here I get two factorized path integrals that now I don't have to match them down here, so I can just solve equations of motion independently and then weigh them appropriately to reconstruct the sum. There's another advantage to this, with which I'm essentially done. I'm essentially done here because what I'm doing is calculating a Wilson loop, and I told you that I wanted to calculate its Fourier transform that defines the probability, the momentum change probability distribution. So, and that requires me to, write it as a Fourier transform. And this is exactly what this Lagrange multiplier is doing. So I am literally if I calculate this object as a function of C, I'm getting my result right away. So now I actually have to, instead of just jumping to the result, I'm going to give you one slide of calculation so that it's not purely magic. The trick is that once you've factored these out and now you no longer have an explicit boundary condition to impose, everything in your path integral only depends on the derivatives of the profile of the string. So I can essentially convert the path integral over the value of the configuration in terms of the derivative, because now there's nothing that refers to the boundary condition, so everything is explicit in terms of x prime. And this now, if you go and look at the action that I'm working with, this is just a function that's directly written in terms of x prime. So taking the saddle point approximation is just amounts to solving algebraic equations here. I'm just extremizing a function. And therefore it's just sitting down, minimizing this, or extremizing this rather, because it's complex, and getting the answer. And that's what you get. You get that therefore that the probability for the momentum to change by some amount is given by some function that I'll give you in the next slide, rescaled appropriately by couplings, temperatures, and times, and I can tell you more about why that precise combination is what has to appear. The result is, of course, complicated. It's not a coincidence that this hadn't been calculated before. If you do the saddle point approximation, get the solutions, and replace back into the action, you get this expression here, which is a complicated integral, and you have to be careful about poles and how you do the contour. But you can do it, and the result you can write in terms of first Appel hypergeometric series. This is that F1. This is just to say that you can get this down to a point where you can just plug it into Mathematica and let Mathematica show you what the answer is. And the answer looks quite nice. So here I'm essentially showing you the exponential of minus this this function I just found. So it's the probability, the momentum change probability rescaled by some factors of square root of lambda t times temperature, so that I get one plot. And here you can ask, well, what's the point of maximum probability? What's the most likely value of the momentum change? And what are the Gaussian variances around it? And you can essentially inspect the result that I showed you analytically and get that, well, if your heavy quark is not moving, there will be no drag force, and you'll have some diffusion coefficients that you can calculate. And if you take the result that I just showed you and do it at a non-zero velocity, you'll reproduce these old results that give you a drag force that has a linear drag coefficient and diffusion coefficients that go as with the same powers of the boost factor. And one thing that's interesting is that as you dial up the velocity, the distribution becomes more and more skewed, which it's already an indication that if you look at the full thing, it becomes less and less Gaussian, which is something that will matter. Okay, now in the last 5 minutes, how do I use this? I did a complicated calculation. I showed you a result that's a nice 3D plot of the transition probability from a state with a momentum p to a state of momentum p minus k. Now, can I actually construct the Langevin type equation that I showed you in the first slide? And well, the answer is just yes. You can essentially do it in discrete time. You can think of this in discrete time steps. I want to evaluate the momentum at a time t plus delta t, and I know the distribution from which to sample the momentum change after some time delta t. There's some conditions that this delta t has to satisfy for me to strictly be able to write this down and take a continuum limit, but let me gloss over those, and you can ask me more later if you're really interested. And because this random variable k is now sampled from a distribution with arbitrarily, with an arbitrary, up to arbitrary non-Gaussian moments, you'll get Fokker-Planck type equation, which we called Kolmogorov equation in our paper, because everything in probability is named after Kolmogorov after some point. It has infinitely many, but it has an arbitrary number of derivatives here, which is to be compared with the Fokker-Planck case earlier, where you only truncate up to Gaussian moments, where you only get up to 2 derivatives here. So yeah, again, these coefficients are just numbers that you can calculate from the distribution I gave you earlier. And if you truncate up to 2 derivatives, you get exactly the equation that I gave you earlier, which does not reach local thermal equilibrium with the plasma. Okay, so let's investigate this now that we have a bigger equation with more features. Let me read. And the first thing that you should notice is that, well, if you want to do an expansion and say, if you want to be consistent with the limits we've taken, which is the fact that the heavy quark is very massive, you should take all of the dimensionful quantities out so that you can see clearly what's leading and what's subleading. So I'm going to take the mass out. And I'm going to get, and if you take the mass out of the momentum variable, you're going to get a sum here that's controlled seemingly perturbatively expanding in T over M. However, the equilibrium solution you're after has the opposite hierarchy. You have an exponential of minus M over T, which means that for every derivative you take of this distribution, you're going to get a factor of M over T, which is going to end up canceling all of these. So you really need to, it's an all-to-all competition that you have to deal with. So, well, that's the problem we're stuck with, so let's get through with it. So instead, I can't just expand the equation of motion. I also need to expand on the solution I'm looking for. So let me expand in this way. Since I know that my leading order term will have a minus m over t in the exponent, let me do this series expansion and start with an exponent of minus 1 up here. And you replace this into the equation I showed you earlier, and you get that the equilibrium condition looks like this. Looks like a sum, essentially, over an infinite number of these coefficients that I calculated earlier, and that the equilibrium solution has to satisfy this. So the question is, wouldn't it be nice if this function here were the relativistic dispersion relation so that we get the promised message? So plug and play. Check for a Boltzmann distribution. The derivative of this is the group velocity, so it's just a velocity. So now you want to check whether the sum here converges to 0 as you take n to infinity. You take the upper limit. So this is n equals 1, and I'm going to do it step by step just to show you that this actually works. So n equals 2, 3, 4, 5, 6. It's slow, and you would not be wrong at suspecting that there's something happening at v equals 1/2. Indeed, but this is converging to 0, which once you've checked visually that that's what's happening, you can now go analytically and just check directly. So you again plug and play. We have explicit expressions for what these distributions are, so you can just check by hand once you know what to look for. So works out, and the equilibrium distribution is indeed a Boltzmann distribution with a relativistic dispersion relation, as you would expect from general statistical physics rounds. So if I go back to the quote from Gupser's paper, what happens is that this is the late-time solution to this equation up here. The only thing that you have to modify or be careful about is that this will not work if you assume that the Langevin equation has a Gaussian momentum transfer. You actually need to take into account all of the non-Gaussian moments of the momentum transfer for it to actually thermalize. And if you were, you can make this work with a Gaussian distribution if you're only looking at the very non-relativistic limit. But as you could see from these plots here, already this is the actual velocity that you'll get in the distribution. So even if you're at 0.2, 0.3, you really need to go higher. So that is to say, life is harder than what you'd expect. You can't just play around with Gaussian random variables as you might like. So, okay, I set up a complicated problem. Now let me actually also give you an answer for it. How much? Okay, I'll just show you a plot then. So short answer is that you can essentially doing the same expansion that I showed you earlier. You can expand in T over M at the level of the exponent of the distribution, and you can get an evolution equation that you can get order by order in T over M. The hard part is that the first one is just highly nonlinear, and you need to sit down and think about it. But we've done that. And so here's some initial condition for the probability distribution of the momentum, not the change, the full probability distribution of the heavy quark momentum. We're initializing it here in this way. There's a p squared here because I live in 3+1 dimensions. So the area under this curve is constant. And I can just play. So indeed, you see that you start from a distribution with the center around a high momentum, and you can see that as time goes by, the mean of the distribution gets stopped, and you converge to the Boltzmann distribution, which is local thermal equilibrium. So it works. That's it. We've shown that things indeed work out as you'd expect. So now once we've set this up for n equals 4, one can think about redoing this for more general theories, and I'm happy to talk about that any moment in the rest of the day. Thank you.
Thanks, Bruno. Time for some questions.
So it takes a long time to thermalize.
Oh, well, yeah, it's controlled by the mass of the heavy quark, indeed. Yeah, I mean, if it's heavy, the momentum transfer that the heavy quark receives is of the order of the temperature parametrically. So the heavier the quark, the longer it will take, yes.
So in the real world, is there enough time?
No. And that's what makes, so if I take so this M over T here is inspired by a bottom quark. So you can think 4 GeV and 200 MeV for the temperature. And if you do the estimate, you'll find that they shouldn't reach local thermal equilibrium in the time of a heavy ion collision, which actually means that you care about the shape of this distribution at intermediate times, because at some point the plasma will fall apart, which means that this distribution will cease being stopped by a fluid, and then you use that as an initial condition for your next stage of the evolution.
What's the status of experimental measurements of this? Do you know?
Oh, yeah.
In QCD, not in N equals 4.
Absolutely. I mean, this is experimental measurements of, so as you can see by the maybe 4th or 5th slide that I showed you, which is like shows you the whole pipeline conceptually of heavy ion collision, you're not going to measure this momentum directly. You're going to measure essentially particle distribution of B hadrons or C hadrons that you can reconstruct by their decay patterns. And really what the biggest uncertainty, I would say, is in theory connecting that final observation of how those heavy quarks flow out with how they're produced. We're going to fill in that gap. So measurements of the flow of heavy quarks are there. You see that they are dragged. You see that how to quantify this? You see that essentially some of them follow the flow of the fluid that surrounds it, so that actually you see that some of them did thermalize, but not all of them. You can play this game for, say, 5 GeV B quarks. You can play this game for 10, 20, 30, and for each of them you'll get different answers, of course. The nice thing about this is that we now have, in a sense, a unified framework to treat heavy quarks in medium all the way from the non-relativistic case to the well-relativistic case.
I mean, is it believed that they don't lose much energy after they emerge from the plasma or after it transitions to hadronization?
Okay.
But there's a fragmentation function in vacuum. And,
yeah.
But that's
at the level of
observables,
what you do is you take ratios, really. You compare PP collisions with lead-lead collisions.
Okay.
And essentially you look at the difference. You look at how much more energy these heavy quarks lose. And of course, the vacuum part of the problem is a problem on its own as well. So you're looking at medium modifications. You're not looking at pure thermal part.
Question over here.
Thanks, a very interesting talk. So I have two questions. The first is that now you have a Schwinger calculus for the Wilson line, and you have a L contour and right contour. So using high ordering perturbation theory, you have an influence function that couple the left and right. Does that lead to a new saddle point solution?
New saddle point. Well, by new you have to tell me relative to what. So one thing I can tell you is that, well, if you go back to the slides where I had the strings in this way, and you want to look at saddle points that satisfy this boundary condition, those saddle points will in general be different to the saddle points that you get by just looking at the single side case. So, I mean, it's not like a settled thing in the sense that like imposing the boundary conditions between all these sides is the hard part of this calculation. Mm-hmm. It's the thing that you have to make sure you got right. And I don't have a general answer how to set this up other than case by case. I mean, I can tell you where we drew our intuition from, which is these works by Skenderis and Van Rees, which is that when you set up the Schwinger-Keldysh contour in holography, you would essentially, as I said in words, you'd have one manifold into the bulk for each segment of the contour. And since this manifold here essentially has no boundary, if you have a string hanging down from this side and here and from the other side, they meet down here. They meet at the end of the cigar here. So all I use today is that this point is the same from all sides. Now, the situation gets more complicated if you want to do finite frequency perturbations. So I got away with many things because I'm doing a uniform perturbation along time, so I'm just shifting the line parallel to each other. If I wanted to introduce fluctuations parameterized by a frequency, then I have to do something more complicated, which is to see how those perturbations propagate into the bulk and how these things talk to each other down here, which is the approach that people started with to calculate these diffusion coefficients, and which is also why they stopped there.
Yeah, I see.
Yeah.
So my second question is that, so for Fokker-Planck equation, we actually have the ambiguity of the ordering where you put the derivative. Do you still have this for your bigger equation, and does that affect the solution?
So I'm going to claim here that I don't have the ambiguity because I have a very well prescribed starting point from the QFT point of view. I have an initial state, and I'm calculating the change starting from the initial state to a final state, and that unambiguously gives me this. If I did the opposite ordering, I would have to work it out. Like let's say if instead I put delta t's elsewhere in this equation, that's your question. We can talk about this later, right? I don't have a straight answer.
Okay, thanks.
You seem to indicate that if you do this expansion where you showed the blue curves alternating, that there's a kind of radius of convergence issue at v equals a half.
Yep.
Is there some understanding of why it happens there? I guess it doesn't matter for the full solution, just the way you've expanded it out.
It's okay. Let's see. You're not going to see it from here, but it's related to the fact that that I have to add another term here. So this function here is continuous, infinitely differentiable. But if I want to write it in terms of the Appel series here, this gets singular as I get to C3 equals 0. So I have to add this other piece here to make it continuous, and well, not to make it. It comes out of the calculation. But when you do this series expansion in moments, what you're really probing is the derivatives of this F1 alone. So there's some. There's already a finite radius of convergence in the series expansion of this to begin with, and I mean we know the complete analytic answer, so there's no problem in just full manipulation. But if you do a series expansion, yes, you're going to see that this stops at some point.
All right, thanks a lot. Any other one more question back here?
Yeah, I forgot the number, but at some point this will become supersonic, but that's not 1/2. It's
supersonic. You mean relative to the c² equals 1/3, or?
Yeah.
Oh, yeah, that's an interesting thing to look at.
So it's not this.
No, I didn't comment on it, and all I did here is calculate the expectation value of this Wilson loop, and it will be very interesting to further explore how this back reacts into the fluid and how that propagates. I didn't do any of that here. So I'm just taking a fluid that essentially receives approximately no back reaction, and you see how the heavy quark propagates. Now then once you have this, you can ask one further question and see how the fluid behaves. That's future work.
So are you saying there could be corrections to this from things like shock waves that aren't incorporated? Is that?
I don't have, I can't rule them out.
Okay.
But this is the answer you get if the fluid is in equilibrium.
Right.
If you add dynamics to the fluid, of course you have to start again and see if your approximations work.
Thanks. Any other last questions? Otherwise, let's thank Bruno again.